Let us solve some problems to understand more about this moment of inertia, and for this we will consider these composite sections. Now whenever we have this kind of composite sections, what we can do is we can divide those composite sections into the smaller areas whose properties are already known to us. For example, we have this I section now. What I can do is I can straight away divide this I section into, say, one rectangle. Then I can divide it further here, saying this is my second rectangle, and I can divide this, I mean, will with this division I'll get this as our third rectangle. So I have successfully managed to divide this I section into three subsections, that is three rectangles. Now whenever we try to find the moment of inertia of these composite sections, we will be heavily using parallel axis theorem. We'll be heavily using parallel axis theorem, and that is why this parallel axis theorem is most used, or the most useful theorem in this moment of inertia. Let us consider this as our area 1, let us consider this part as our area 2, and this part as our area 3. Now all these three sub all these three areas 1, 2 and 3 are nothing but they are rectangles. So the centroid can be easily located, and it will be exactly at the geometric center. So for the rectangle 1, the geometric center will be exactly at the center. It will be somewhere here, it will be somewhere here. Then similarly, the centroid of this second area will be exactly in the center, it will be somewhere here, and the centroid of the third area will be exactly at the center, it will be somewhere here. So first centroid will be exactly in between, second cent second centroid will be somewhere here, and the third centroid, that is the centroid of this third rectangle, will be somewhere here. And then if I want to calculate the moment of inertia of the first area of this first rectangle with respect to axis 1 1, with respect to this axis 1 1, then I can very well use parallel axis theorem. So before that, let me just mark this distance. I will call this distance from this centroid to this first axis as y1. I will mark this distance from the centroid of the second element to the to the to the reference axis 1 1 as y2, and this distance we'll call it as y3. So I have y1 is the distance between the centroid of first rectangle to that of the reference axis 1 1. Y2 will be the distance between the reference axis 1 1 and the centroid of second rectangle. Similarly, y3 will be the distance between the reference axis 1 1 and the centroid of third rectangle. So by using parallel axis theorem, I know that the moment of inertia about the reference axis 1 1 will be equal to the moment of inertia of this first rectangle, which I can very well write it as I self 1 plus the area of this rectangle A1 times y1 square. This is nothing but the moment of inertia of this rectangle about this reference axis 1 1. Similarly, if I proceed, then this is for first rectangle. Similarly, if I proceed to find out what will be the moment of inertia about the axis 1 1 for the second rectangle, then again it will be I self, that is the moment of inertia about the centroidal axis of the second rectangle, plus area of the second rectangle multiplied by the distance square. And similarly, I11 for the third rectangle will be I self of third rectangle plus the area of third rectangle times y3 square. Now with this, if I want to find the moment of inertia of this entire I section with respect to I11, then it will be equal to summation of all this I self, where I self summation of all this I self, where I goes from 1 to n, in this case this n is 3, plus ai yi square, again this summation where I goes from 1 to n, in this case n is 3. So this is one formula which we'll be using very frequently to calculate the moment of inertia of this I section. Similarly, once we find this I11, then to find the moment of inertia about the centroidal axis of this entire I section, for that first we'll have to determine y bar of this I section, and the centroidal distance y bar can be found as summation of ai yi divided by summation of ai, which we had seen earlier. The moment we find this centroidal distance y bar, then I can again use this parallel axis theorem as I11, that is the moment of inertia about this axis 11. This will be equal to I xc, that is the moment of inertia about the centroidal axis of this I section, I xc, plus it will be the summation of all the areas, that is the total area of this I section, multiplied by y bar square. So this will be the second formula by which we'll be able to find y bar square. So this is the second formula by which we'll be able to find the moment of inertia about the centroidal axis of this composite section. So we'll be using this formula, and we'll be using this formula. We also need to use this formula. So all this we can do very easily if we construct one table in this fashion. Fine. So here in the first column of this table, we'll note down the number of components. In second column, we will write down the areas of the each component. We will add them up here. This will be the summation of this. Then we'll find the centroidal distance y1, y2, y3 of each components of this each components. Then we'll multiply this area multiplied by the centroidal distance, which will give us later on the y bar. Then I will find out this component area multiplied by y square, which will be used here, and then finally I self of each component. So let us see. So I have divided this composite I section in this fashion: first component, second component, and third component. Then I can write them first here. We have three components here: 1, 2, and 3. And the area of the first component is this. The area of this first component is 20 multiplied by 100. So 20 multiplied by 100, this will be 2000. Similarly, the area of second component will be again 20 multiplied by 100, which will be again 2000, and this will be 20 multiplied by 200, so this should be 4000. Fine. So the centroidal distance y from 1 1. So basically what this means is we need to note down the values of y1, y2, and y3. So y1 is, so this is from here to here, this is 20, from here to here it is 100, and from here to here it will be 10, because the centroidal distance here will be exactly at the half of its height, that is half of this 20. So this distance will be 10, from here to here this will be 10. So this is 10, this is 100, this is 20. So this total becomes 130. So y1 is 130. Y2 will be 20 plus 50, so this will be 70, because this is 20, and from here to here this will be 50. So the total distance from 1 1 to this point will be 70. Similarly, the third distance, centroidal distance y3, will be right from this reference axis up to this point. It will be half of 20, and that will be 10. Now if I add this up, this should become 4000 plus 2000 plus 2000, this should become 8000. Then this is nothing but this is the multiplication of column 2 with 3, that is A with Y. So 2000 multiplied by 130, this will be approximately 260000. Similarly, A2 multiplied by Y2, this will be 140000. This 3 and this 40, so there are 4 zeros here, correct? And then this will be 40000, 4000. And if I sum them up, this the total should be 440000, and this is nothing but area multiplied by this y square. So I need to square this term first and then multiply it with 2000. So this will become 2000 multiplied by 130 square. This will be equal to 33,800, and then 000, 5 more, total 5 zeros, so 33,800,000. Similarly, this will be 2000 multiplied by 70 square. This will be equal to 98,000,000, and then finally this term will be 4000 multiplied by 10 square. This will be equal to 40, and then 40, and then 4 more zeros. So this is what we get here. So the ay square term of the first component is this value, ay square term of the second component is this value, and ay square term of the third component is this value. So if I add these three values, I should get 44,000, and then three more zeros, 000. So this is the total of this term, ay square term. And then finally I self. So I self of the first component will be bd cube by 12. So b here will be this term 100 multiplied by 20 cube by 12. So b this term I self should be bd cube by 12. So for first component it will be 100 multiplied by 20 cube by 12, and that value should be equal to 66667. 66667. Of course this will be approximate value. So this term, similarly this term here, it will be b will be 20, d will be 100, so it will be 20 multiplied by 100 cube by 12, and that will be equal to 16666, and then one more 6, and then 7. And similarly this term bd cube by 12, so here b will be 200 multiplied by 20 cube by 12. So this value here it will be equal to 1,33333. So these are the three values of I self, and then finally I want the summation of this. So that will be equal to 1866667. So we have almost got all the values here in this column. I have got summation of a into y square, so I have got this value. Here in this column I have got summation of I self, so I have got this value. So I am good to find I11. Also I'm good to find y bar, which is summation of this column, that is summation of ai yi divided by summation of ai. So first let us calculate what will be I11. So I11 will be equal to summation of I self, that is this value 1866667, plus summation of ai yi, that is this term, a summation of ai yi square, that is this term, that will be equal to 44 1 2 3, again 1 2 3, and this should be equal to 458 6666, and then 7. So So let us just count these numbers: 1 2 3 4 5 6 7 8, and this should be 1 2 3 4 5 6 7 8. All right, so this is what we have got, and the unit will be mm raised to 4, because all these units here are in mm. All units are in mm. So this is what we get I11 from this table. Then the then we need to find y bar. Y bar is the summation of ai yi divided by summation of ai. So summation of ai yi is 44, and then 4 zeros divided by 8,000. So this will be equal to y bar term, this y bar term will be equal to 55 mm. 55 mm. Now finally I need to find the moment of inertia of this section about the centroidal axis, that means the axis which passes through this centroid. I found that the centroidal distance y bar is 55 mm from this reference axis 1 1, so it is at a distance of 55. This is 20 and 35, so it will be somewhere here at this point. So basically what I need to do is I need to find, this is our point C, centroidal point. I need to find what will be the moment of inertia, what will be the moment of inertia about this axis, provided I know the moment of inertia about the axis I11, which I have already found. So what I can do here is I can again use parallel axis theorem. I can use parallel axis theorem, and that theorem will be I11 I11 will be plus IXC plus summation of areas multiplied by y bar square, and I have all this data with us. So what is I11, which we have already found? So this will be 4 5 8 6 6 6 6 7 equal to Ixc is the quantity which we need to find, that is moment of inertia about the x-axis passing through the centroid, plus summation of area is 8,000, multiplied by y bar square. Y bar is 55, so this is 55 square, and then if I take this term this side, I will get Ixc as 21666667 mm raised to 4. So this is this moment of inertia about the centroidal axis of this I section. Fine. So this is how we can use the parallel axis theorem. We have used parallel axis theorem at this point. We have used parallel axis theorem at this point. We have used parallel axis theorem at this point. We have used parallel axis theorem at this point. Also, we have used the formula to calculate the centroidal distance. So this, if I can find these three things, I can solve any problem of finding the moment of inertia of this composite sections. We have here one more problem. I have here a L section, and we need to do the similar analysis for this. We need to find the moment of inertia about the centroidal axis xx as well as yy. So if let us assume that the its centroid will be somewhere here, we will obviously will find that. Then I need to find what will be the moment of inertia about this centroidal axis xc and yc, and let me call this point as C. And for this again we can do same thing. The way we had taken here one reference axis, we will take here two reference axes. One reference axis passing through the bottom boundary, and I will name it as 1 1, and then I will take one more reference axis passing through its leftmost boundary, and I will call that axis as 2 2. And first what we'll do is we will find the moment of inertia about the centroidal axis xx, the way we had done all these steps here. The same steps we need to follow here. Now what we will do is we will divide this L section into two components. If I divide this here, I have this as the first cross section and this as the second cross section. So I have here only two components, 1 and 2. The area of the first component will be 100 multiplied by 20. So this will become 2000, and the area of the second component will be 60 multiplied by 20, which will be 1200. Since this is 80 and this is 20, from here to here this distance will be 60, so 60 multiplied by 20 will be 1200. The centroidal distance of this area with respect to 1 1 will be half of this 100, which will be 50, and the centroidal distance of this component 2 with respect to the axis 1 1 will be 10. Hence a into y, this area multiplied by centroidal distance y, will give us 10, and then this will be 3 zeros and this will be the fourth zero. Similarly, a2 multiplied by y2 will be 1000, will be 12,000, this 12, this two zeros and one zero. Then a into y square, area multiplied by y square, will be equal to 50, and then three more zeros and then one more zero. So this will be 50,000 and one more zero. And then similarly, area a2 into y2 square will be equal to 12 and then four more zeros. So I self, that is the moment of inertia of the first component about its centroidal axis, will be nothing but b d cube by 12. So here b is 20 multiplied by d is 100 cube by 12, bd cube by 12, and that will be equal to 1666667. And similarly here for second component, b will be 60 multiplied by d will be 20 cube by 12, and that will be equal to 40,000. Let us add these quantities. Here we don't have the third component, so I've just left this blank. So summation of area will be 3200. This summation is not required. Summation of a into y will be 112,000, and summation of ay square will be 512,000, and the summation of I self will be 170,666,7. Once I get all these quantities, now we need to find moment of inertia about the axis I11, which can be found using this formula. That is the I11 is summation of I self plus summation of area into y square. So summation of I self, what we have got is 17,0667 plus summation of ay square is 512,000. And if I add these quantities, I should get this as 68,26667 mm raised to 4. Again, all these units are in terms of mm. So this is what we got, but I need to find moment of inertia about the centroidal axis xc. So again I can use the parallel axis theorem, which can be written as I11 will be equal to Ixc, that is the moment of inertia about the centroidal axis, plus summation of area times y bar square. Fine. This will be equal to I11 value we have already found, so that is 682667. Ixc is the centroidal moment of inertia which we need to find, plus summation of a is 3200. This summation of a is 3200 multiplied by y bar square. Y bar is what we need to find now. So y bar can be found as summation of ai yi divided by summation of ai. The summation of ai yi is 1,1,2,0,0 divided by summation of ai is 3,2,0,0. And if I calculate this, y bar will be approximately 35 mm. Now if I substitute this 35 mm here, so this will be 35 square. Now if I take these values this side, I should get this IXC as 29,06667 mm raised to 4. So this is the moment of inertia. This is the moment of inertia about the centroidal axis XC. Then we need to also find the moment of inertia about the centroidal axis YY, that is the vertical axis, this vertical axis. So I need to locate the moment of inertia about this axis YC passing through this centroid. Moment of inertia about this axis we have already found out. So this is done. So I need to find now the moment of inertia about this axis. For this, my reference axis will be this 2 2. And then we need to do similar exercise again. So this will be my first area, this will be my second area. I have two components, 1 and 2. The area of the first component is 2000, that is 100 multiplied by 20. Area of the second component will be 60 multiplied by 20, that is 1200. And then this distance, centroidal distance x from 2 to, I need to find this. So this is nothing but distance between the reference axis and the centroidal distance. This distance will be 10, whereas the distance between this centroidal distance and this will be equal to, this is 20 and this will be 30, this will be 30, so this will be 50, so this will be 50. And then area ay is nothing but area multiplied by this distance, that will be 2000, and this will be equal to 6000. And then we need to find area multiplied by x square, that is 2000 multiplied by 10 square, so that will be 2000 and then 0 and one more 0. Then this will be 1200 multiplied by 50 square, that is 300, and then there should be four more zeros, 1 2 3 4. So this is the a into x square. Then we need to find I self of this first component with respect to y-axis. So with respect to y-axis, IY will be 100, that is this will be now b 100 multiplied by 20 cube divided by 12, bd cube by 12. So then this will be equal to 66667. This will be, I self will be db cube by 12 now, because this will be d and this will be b. So 100 multiplied by 20 cube. Similarly, the I self of this second component will be 20 multiplied by 60 cube divided by 12, and that will be equal to 36,000. So this will be the moment of inertia of this second area. And then again we need to sum this up. So this will be 3200, this will be 80,000, this sum will be 32,000,000, and this term will be 42,66,67. From here, from here I can very well now find I22, that is the moment of inertia about the reference axis 22, as sum of this I self, that is 426667, plus sum of this ax square, that is 32,000,000, and then if I add them up I should get this as 36,26667 mm raised to 4. Then if I want to find out the moment of inertia about the y-axis passing through centroid, again I need to use parallel axis theorem, and that will be I22, that is the moment of inertia, about this reference axis 22 will be equal to IYC plus summation of area multiplied by x bar square, so I22 is the value which we already know, that is equal to 362666. This is the value which I need to find, plus summation of area is 3200 multiplied by x bar square. Now x bar can be found out as summation of AIXI divided by summation of AI. Summation of AIXI will be 80000 divided by summation of area is 3200, and if I calculate this value should be equal to 25 mm, so this x bar will be 25 square. Now if I take this value again this side, I should get this IYC as 16 to 666 7 mm raised to 4.